through some of the applications of these methods for the easier case, the median strike slip case, okay? And you'll see how we're trying to get at that. And we've added some plots that I hope address questions on that people have asked. So first of all, on the median models, what we are doing, we had looked at our set before. On the left-hand side are the GMPEs that we had selected as candidate models, and then we are breaking them down into our 4 source classes. Strike slip at short distances, big magnitudes. Reverse at short distances, again, large magnitudes. Remember, we had the normal faulting host zone events, and then the large distant events several hundred kilometers away. So for Diablo Canyon, it's the 2, and we're talking now just about the strike slip part. So dips between 70 and 90, magnitudes greater than 5, and distances less than 20 is really where our focus is. So our deaggregation shows that if we capture that, we've captured all the important things to hazard. So the models we are keeping, Grazer and Calcon, we're keeping it separate because it has a functional form that is not well represented by our common model. It has a different distance attenuation that increases in the short distance range and then falls off. The Zhao model is also included. There's a Zhao et al. Modified that's in there, and I think we got some comments back from our reviewers in terms of are we implementing that right? And I think the answer is we're not. So that model is not a model that Zhao has built. We have been using this concept, but I'll show you a plot as to why we probably need to do that model differently than what we've done. Then there's the 5 NGA models. The one model that we were having an issue with was Idris's model at 1 kilometer was producing an unusual spectral shape. So in developing these maps, we've used it from 3 kilometers on out. Akar is also included, and Bindi is not included because it didn't have consistent magnitude scaling. Remember Bob showed the other day, it has at 5 hertz suddenly a break going up with really strong magnitude scaling that isn't seen in any other models, and fundamentally doesn't bring us new information for large magnitudes, which is what our focus is here. So the Zhao model, one of the issues was, if you remember, the modification that he had talked about was a concept. He said he doesn't see strong magnitude scaling or above magnitude 7.1. We were treating that as one way to capture the end member was above magnitude 7.1, no magnitude scaling. So in running the calculation, if we got a 7.3, we simply would plug in a 7.1. That doesn't work, and the reason is Zhao's model was no magnitude scaling in the event terms. But that was relative to a magnitude-dependent geometrical spreading term. So what's shown here in blue are Zhao's 06 model for magnitudes 6, 7, and 8. And you can see as I'm going up, you're flattening out the geometrical spreading, right? So that's the magnitude term in front of, that was the A6 term, I think, that Nico had shown earlier. But when we're trying to say there's no magnitude dependence on the event terms, that would be the scaling of that model up or down. So what we really should be doing to run that model for magnitude 8 is to use the magnitude 8 geometrical spreading part, but the constant from the magnitude 7.1. And that's what's shown by the red line. So we need to redo that, and I think then we would have a model that's consistent with what Zhao found, but it doesn't lead to no magnitude scaling, which then I think makes the rest of us feel a little bit better as well as to what's going on, right? So it's not saying it's not any different, it's just back in here, he's coming to a full saturation at all periods, which most of us have not found before. So at short periods, we would say that's already consistent with what we found. At long periods, that's a different model. Okay, going forward, when we look at Zhao right now, the Zhao modified model is not going to be implemented quite properly. And so but you'll see what's going on. Okay? Grazer and Calcon's model, the issue that we've talked about before was the publication status, and I talked to Vladimir this morning a little bit just to double check. So this will be published in the National Conference on Earthquake Engineering this July in the proceedings. There was a USGS open file report under review. It's not clear that that will be published going forward, but we have the model. We're using that model separately right now because of its different functional form. So it's not part of our covariance matrix on the coefficients, and we can bring it along the same way we talked about the other day of plotting the other models that we're not using in our Salmons maps anyway, just to see where they fall. So let's look at the issue again of the published GMPE and the common functional form. So Nick showed you the impact on hazard, and this is just an example on the left, magnitude 5 and magnitude 6. There's two things that are shown here. Actually, I'm going to jump here where you can see the legend. So ASK and BSSA, so this is ASK is a rupture distance-based model consistent with the common form. BSSA is a joint bore distance model that's going to be inconsistent with that form. So the differences in the distance metrics will be a mismatch here. At magnitude 8, you can see we're matching. In fact, the models are very similar, but they're matching very well. Magnitude 7, there's not much distance or difference either. That's not a surprise. Vertical strike slip faults, joint bore distance and rupture distance are going to be the same when the earthquake's big enough to rupture to the surface, so everything's working. If we go back, so the dashed lines, remember, compare green to the, is that purple, I think, on the bottom, but I'll point it out to you. If we go here, you'll see close in to magnitude 5 is where the green line starts to deviate from the purple. Okay, purple is our common form using rupture distance. If my magnitude 5 is close in but at depth, the joint bore distance will say that's the same, it's at 0, right? But our rupture distance will say it's further away. And as a result, it's going to create a model that's going to come down a little bit. It can't match that whole curvature because of the different distance metrics. That's just what goes on. So this is the kind of misfit that we're going to get. If that's the most important range for us, okay, for magnitude 5, then we would really worry about that. But magnitude 5s at 1 kilometer aren't going to be our controlling source here. We're going to be controlled more by things over magnitude 6. This gets back to Bob's question as well. How do we define what are we trying to match? Okay, so by the time I'm at magnitude 6, now there's not that much difference because the sources are big enough in the rupture dimensions that the joint bore and rupture distances are very similar. Okay, is that good? John, that's what you were, okay, all right. We can look at 1 second, same picture happens, and I would, if you're looking at the comparison between the red and the dotted blue line, that's just parameterizing ASK to the simple model, and it works because the models are very similar in their parameterization. Where things start to get a little different here, remember this was only fit out to 30 kilometers. When you extrapolate that to larger distances, things are going to go different, all right? And we may find, we'll see some of the realizations really different out here at larger distances. What we did in calculating the hazard for now, we simply eliminated anything more than 30 kilometers away because we know we're controlled by within 15. But we'll probably have to generate these common forms over a larger distance metric or distance range, just so we don't have a funny upturning of the model, because when you extrapolate any coefficients outside their range, you can get unusual behavior. Okay, and that's what you're going to see. But the same feature here, magnitudes at 1 second, it fits our basically common here. We do have a little bit more of a difference in the magnitude scaling, okay, and that's basically coming into exactly how things are breaking and in the scaling in each of the ranges. But it's here, say, a 10% difference in this range. So that's the limits there. So now, if we take those and then say, where do these things plot? So we generated, Nico I should say, Nico generated 1,000 models, and that defines the space. So those gray points aren't shown, but the space that they occupy is the colored part, right? So part of this is forget their density and where they're centered. Just now, this is the space of models that we are considering. Probably bigger than the space of allowable models, which is good. We want to start and not be missing something, and then we need to work from there. John, do you have a question?
If the colored space is the space that the models occupy, why is there a dot outside of that space?
Simulations. So we're going to
that's a
get to that, okay? So that's an important issue, right? So that's the space of the, we started with the red models, right? The red models generated this space, okay? Went too far. But then we also have put in the Grazer and Calcon model and just plotted it. That's the green point. So it was not used in developing the 1,000 models, but we can compare where it shows up in ground motion space, okay? Then we also put in the 3 simulations. Okay, so for this case, it's not magnitude 5s and larger, it's a smaller set. So this is just for the vectors for which we had numerical simulations. Okay, so that's why these are a bit of a different shape. It's a more limited range. It's a 6 point, can you remind me, Nico, what the magnitudes are?
It's 6.6 and 7.2.
So this is big strike-slip earthquakes. What do the models look like? And now tell me which model is going to be outside here. You should know from what we saw the other day. High frequency, big magnet. Which model stuck out different at the high frequencies? XSIM. So that's XSIM, all right? So we saw that was higher than any of our predictions. It's coming up steeper at short distances, right? Creating a higher value. The other two in here are the 2 models from San Diego and Graves and Patarka, and I forget which is which.
No.
Yes.
So these are the GMPEs based on simulations, right? GMPEs developed based on a specific simulation.
We generated the simulations. Those
And
were
then
points. They were
fitted-
then reparameterized
Right.
with a simple form.
That's fine.
This form is even simpler. It's not magnitude dependent. He just fit it. And so we had a form for the magnitude 6.6 and another fit to the magnitude 7.4, if I'm saying that right. 7.2. Okay. And now we filled the vector with smooth coefficients.
Yeah, that's
Okay.
fine. So I think the idea came from Brian yesterday during the break. He was suggesting, what about you put those 3 new GMPEs in the original seed
Yeah,
and
so-
do it again?
Right, and so if we did that, that would create models down at the bottom. Answering John's question as to why did we miss those, right? So currently, we've been using the simulations as a check at the end, as opposed to a piece of the model going forward, partly because we only have it for a limited number of cases, right? That's really what's going on. So we could use that, but now I need to create my model not just for magnitude 6.6s and 7.2s, it needs to be for the full range. So options are to bring along some of the simulations we have at smaller magnitudes and create a full GMPE, or use them in this way here, okay? This would tell me now, comparing these, I would need to be broadening out my distribution if I'm going to capture XSIM that I would have missed if I had just been using my simulations by themselves. Okay, the black point is the average of where those 1,000 models would be sitting. Okay. So this is now, okay, and so this tells you SDSU was the higher one, Graves and Partucker down here. Let's go back to what's in the background, the contour plot. It's the mean residual of the event term. So it's like the constant shift we get comparing the subset of data used here to these model predictions, okay? So if we do that, the 0 line is here, which is going, I think it's that one, right? Okay, now you could say, why don't they all fall on 0? Because they're using different subsets, and we've computed the event terms from this subset that doesn't have the more distant data in there as well. So the event terms may not all be identical, but if we had done this for the set that was used for say, the Campbell and Bazorgnia model, your model would fall right on the 0 line, right? Then if you looked at my model versus my set, it would fall on the 0 line, assuming we've done our regressions properly. Okay? So what are the ranges? So part of this is, we're back to how do you interpret this space, and there's been continuing issues. What does the space mean? So the background information, the contour plot, gives you some way to think about what's happening in that space. So each one of these steps is a 0.2 change in the ground motion, 20% change in the medians. Okay, did something just move? No. So if I'm going from here to 0 to there, the models are falling in the range of 0 to minus 0.2 on the values. Okay? Why would that happen? What's a negative residual mean? Under prediction or over prediction? Over prediction. Does this make sense? What have the data been trying to tell us to do at big magnitudes for years and years, and we refuse to do? Oversaturate, right? The data tell us bigger magnitudes are creating lower ground motions, and we say, no, we're going to keep our models fully saturated, but not oversaturated. So it's not a surprise from this subset that we're sitting biased high. Okay, so these things are making sense as to where they sit. How are we going to weight these things going forward? Do we allow oversaturation moving this way or not?
If you show the similar thing for period, say, 3 seconds, you should not see that.
I think I have a 1 second here. So Nico gave me a whole bunch of them, and I'll run through some of
Okay.
those. Okay? Okay, so I want you to be able to see there's something here, all right? This is not just some abstract mathematical concept, but you can start to interpret what's going on these plots, and this is a way of making a continuous space of ground motion models that we can now discretize into a small manageable set. Our job is putting the center, okay? When we say center, body, and range, where are we going to center our models? The range, how far out are we going to allow it to go? Do we go all the way out to the edges? Or are some of these physically unrealizable or so far out that we don't accept them? And the body is, are we going to use a symmetric or asymmetric distribution of those weights? I might say here, if I'm working in this range, I could say I'm going to be here and I'm going symmetric, or I'm going to be going asymmetric, depending on what's happening to the data sets and where the simulations are. So right now I have one simulation over here, which is SDSU, that has essentially consistent with the oversaturation, if you want to look at it that way. Graves and Petarka is keeping stronger scaling going on for this subset of calculations. Okay? The Grazier and Calcom model is over here because it's coming back down in that range. And so it's not surprising. We saw from Nick, it had lower hazard calculations, right?
Norm,
Yeah.
can you remind us again what data set you used to calculate the residuals?
This was my selection, but what magnitude range did you cut off for this set, Nico?
So that's magnitudes 5 to 8 and distances 0 to 70 kilometers. And BS30 values above 250,
Okay.
corrected to 760.
So-
Does it include Chi-Chi and
Yes.
it include Chi-Chi earthquake?
Well, it's strike slip only.
Yes,
So,
right,
so
strike
Chi-Chi
slip.
is not in here.
Okay, all right.
So this is not the full data set that was used, right? And that's part of it. We're trying to isolate the data for this particular case. So it's a smaller data set. It's not clear. We want to be centered on 0. Because when you build the models, the GMP developers use more than the small set of data that applies to this particular condition. Right? And back to you're borrowing strength in the scaling and magnitude from the reverse events to help you tell how to strike slip event scale and so forth, right? So there's other things that are going on beyond trying to find the best non-parametric form that fits this particular subset of data.
So Norm, presumably if you use the data set that's limited to one event that's well recorded, you could compare the event term you observe on this map to the modeler's event term and get a verification that it should be about right.
Can you,
Am I not loud?
you're not loud enough, so I
Wow.
can barely hear you.
This is weird. Okay, so it's a question more conceptual, but that's probably for Nico. But if, say, you plot your GMPs in a space where the data set is defined by one event that's well recorded, so you can have a good data set, then you could get an event term from this here, and as a modeler, you could go back and check if that event term was there. You could have a single event term that should match on this map what you've computed with your regression. One event, lots of data. Say you were doing Chi-Chi.
Okay, so I have Chi-Chi.
Chi-Chi and
In this map, Chi-Chi is 1 point because it's
Oh,
an
you're
event
right.
term.
You're right, it's
Yeah,
the event
that's
term.
not going to help us.
Okay, thank you. That clarifies that.
So the other part
Yeah.
we want to look at, if you're going to look at lots of recordings, that's the likelihood. Yes. Okay, so we're bringing the
That's what I
distribution
mixed.
in there.
Thank you.
Okay, so it would be more on this plot is what you were just talking about. So now in the likelihood space, what's going on? So there's a big broad range. We're back to Ed had mentioned, explain what these things are on their axes, okay? So the contours now are contours of the log likelihood, right? So that's the log of the joint probability of these data having been generated by the model. And at each point, we compute that. So because the probability of any 1 point being generated is less than 1, the log of any number less than 1 is a negative number, right? So we're going to add up a bunch of negative numbers, so that's why the scale is negative. Bigger means higher chance that the model generated the data. Okay? And we're looking at a big flat area where all of these models are about equally likely to have made the observations. But when we go off here, we can say we're crashing down on these sides and on these. So we can start to think from this data set, it would be telling me to chop off those edges. Okay? Then I want to repeat that process for another subset of the data and see if it keeps telling me the same parts should be thrown out.
So, Norm, hypothetically, if
Closer to your mouth.
if this was the final map, you would assign equal weight on the if you wanted to use the original
So, yeah,
GMP.
you could say in here, this big zone, the likelihoods are all the same. Okay, so I might say these areas here should all be similar weighting. I could divide those into 3. I could also go back and look at it in here, and you can see that's also parallel to the sort of the contours of the mean bias. What Gabe asked us to do is to turn all these plots, just rotate them sideways. So in this vector here, these things would always be, let's say, running vertical. So I could rotate this thing a little bit counterclockwise. And if we made it that way, then the x-axis direction would always be changing in the median. All right, to give you sort of a reference point, so if we go from one map to another, you always can be thinking horizontal means a certain change. Vertical, then, is directions in the vertical would be different magnitude and distance or depth scaling effects and so forth. Okay? Is that clear what we're trying to do? And why? Clearer, clear. So Ed says it's clearer, so that's good. Okay. The issues here we're going to face is models that are outside here. So the XM is producing much stronger high-frequency motions at short distances in the magnitude 6.5 to 7 range than the other models. In that model, when it went up to bigger, what, 7.4 or larger, I think it started to come back down again. But that's a feature that we need to say if that's a credible model. It's near the zero line, so it's not too biased, but it's creating different distance scaling. And in fact, because we know this is different at short distances, we know that this is the direction, or confer, of a steeper slope in the distance scaling between, say, 10 and 0. That's what's happening there. In our context, that would be like using a smaller fictitious depth. It would do that, right? It's the same fit everywhere else, but in close it brings it up. Okay? Good so far? Yes, okay. All right. So, yes. Was there?
Can you go back to the residual plots? Okay. Now, if you extend the zero line, the zero contour line down, would it pass close to that XM?
I think so. That would be my, just based on how we've seen these going before. Because what is XM doing, Brian? It's looking at, I could be looking at the mean event terms, but those aren't controlled by 1 to 5 kilometers. There's a lot more of the data out at, say, 10, where XM is similar to the other models.
Okay. So the fact that XM is not within this bound is because of how to scale with distance and magnitude at short distance.
Correct.
It's
And
different from the other models.
essentially, I would say their fictitious depth term is smaller.
Okay.
That's the way I've been thinking. So if we had put that into the first set of covariance matrices, you would have made a wider range of smaller fictitious depths, which would have then created more models with a steeper slope right in the short distances. Okay? Ed, did you have a question? Oh, okay. So the part of the question is, would this extend down? Really, we need to create these models going further down here, and either by bringing these in first, but we need to get the space to here. This tells us I need to expand my space of models to capture the XM model if that is going to be considered a credible model. All right, we asked Gail about this and said, why is it going up? And her response was, well, she thinks that this could be the correct behavior, and if we get enough data in close on rock sites, that this might be the model that comes out. So she's seen this before. It's not an error in our calculations, and she considers it that her model is working as intended. All right, now it's up for us to also evaluate that part of the model. It's not working.
You see on the likelihood plot, though, that there is likelihood region
Right.
coming in and sort of cutting it off.
Right, so the contours on the likelihood are not just parallel, but they're starting to come around here. Right, so that would tell you it's a much lower, less consistent with the observations than the other models.
And Norm, the difference between the magnitude 7.2 and the 7.4
You need
case,
to really speak
for
loudly.
XM?
Yes,
you said that for the magnitude 7.4 case that it's coming down. It's not that XSIM's coming down, it's that SDSU's also going up. for the
Okay.
7.4 case.
it's not as.
Jeff just confirmed that.
It's
so-
not as far off on its own
Yeah.
as the other models. Right. Okay. So I think I've got this right, Nico. This was the distance from the center. Right. So there's different ways you can do this. So if we had, there's a whole lot of models there just sort of piled together, and if we look at this space, you could say, how far away am I moving from the center? If everything was ideal, and you could take your two-dimensional vector and get all the information on, your high dimensional vector and get it on 2D, these would be perfect circles. Is that a correct? So Nico's saying yes. I get a gold star for the day. Okay. The variations in this are, I think, maybe getting a little bit to what you were talking about, Jack, is how do you measure the ability of the model to actually reproduce that? So the deviations from circular here are the misfits. We can still, though, put in a vector or a metric that says what that number is. Okay? So right now, this is saying at a single frequency, it's doing a pretty good job. Okay. All right, if we go to 1 hertz, you were asking about 1 hertz, right, Yusuf? Okay. We're rotated, okay? Now we're 90 degrees of the way we actually are going to want this thing, okay? So moving this direction is changing the median. So where is 0? Right in here, between light blue and the darker blue. So through this line. Is it? This one, yeah, I'm sorry. Right there is the 0 line. Yeah, and you see now the models are closer to 0, and as Yusuf said, less oversaturation. We don't have such a big deal of oversaturation in the longer periods, and we're fitting the data, right? So we're more consistent with the observation. The simulations are up here in blue. They're all in one direction. Why? And when we did the validation, what did we see at long period over and over? They were higher, right? So this is just showing you what we saw in the validation exercise previously. At long periods, the simulations are higher. What is higher? Higher is moving in this direction here, right? That's moving to a higher value. So the plots are showing us what we already knew, and we're putting it in a more organized way.
Are you sure? So the darker colors at the top are positive?
Yes.
I
Is it
thought
the
they
other
were-
way? Oh, I'm sorry. Then I've got did I do 3 seconds too? Let me see, because then I'm going to tell you something wrong. I suppose
Before they were negative.
These are negative residuals. I'm sorry.
So that means the,
Thank you. Over predicting, so we get a negative residual. See, thank you for reminding me what negative means here, right?
but well, I can't remember at 1 second, but at long periods, the simulations were over the GMPEs, so the
Right.
residual should be positive. Data minus model. If you take the simulations as the data and the GMPs as the model.
Right? And the model is bigger. What's data minus model as the model gets bigger?
Are we considering the simulations the model or the data?
The model.
The model. Oh, okay. So then it would be negative. Okay.
Okay? Yeah, and so
was
I
thinking
had
of the simulations as
had
the
myself
data.
confused as well. Negative means when a model plots in the negative direction, as it's going more negative on the residuals, the model is higher, right?
The simulations overpredict.
Right.
Yeah. Okay.
Okay? Wait, you need to use the,
I assume you're getting worse if you go to 3, 4, 5 seconds.
I didn't put those plots in here because I'm
That's fine.
trying to keep it,
That's fine.
but yes, you would see a difference, okay?
I wouldn't use the word worse, I would just use the word different.
Different, more, yeah. They are providing different information. Now, what's the right thing to do? Here's the likelihoods, okay? So there's a big broad range there. Those models are falling in those likelihoods. We're finding, in this case, the Grazier model is sticking out, okay, and it pops out in the hazard calculation. Okay. But these are all sort of aligned in this direction, meaning they're all centered kind of on the data, and they're going to have different magnitude scaling going on, okay, or distance scaling.
And these, just like the high frequency plot, the likelihood contour is oriented roughly parallel with the 0 mean line.
Right.
So they're
Yeah.
they're consistent in that sense.
So that's fundamentally that's saying there's a range of magnitude and distance scalings that fit the data almost equally well. And the magnitude and distance scalings are being stretched out here, and the likelihood says all that stuff is equal good fits. You could change C2 and trade off with C3 and get almost the same values, right? So that's what we've known, that's our difficulty in the regressions. Okay. How much time do I want to, let me jump to the ahead a little bit here. Okay. So we get to this with, instead of one period, all periods, and it gets more difficult.
Quick question, the plot you just showed before, the likelihood is 5 hertz, okay? Didn't you show another one earlier, and maybe I'm just sniffing glue again, but where...
That's a 1 hertz. I didn't fit this because I was copying and pasting. That's 1 hertz because they go together.
Okay, because the other one was where the likelihood was curving down and XSIM was outside.
Yeah.
So this
Sorry.
is 1 hertz.
1 hertz, and this should
Okay.
say 1 hertz as well.
Thank you.
Okay? And you can kind of tell because the shapes have to be identical, right? These shapes are... All right, sorry about that. So if we go to all of the periods at once, we get a less pretty picture, and this is getting, I think, to the point that it's harder to take a high dimension with now 5 periods and map it into the 2-dimensional space. And I didn't show the circles. I should have done that. They're not as circular, so they're having a harder time. Nico, did you want to add something to that?
They're still fairly circular, but the thing is that the models don't predict the data at each period equally likely or equally well.
Yeah.
So therefore you get maybe a higher misfit at 100 hertz, a medium misfit at 1 hertz,
Right.
and this just gets averaged out in this plot.
So when a model has the strength, is it fitting the data at the high frequencies but missing at the long periods, they get all the likelihoods start to average out, and you can see less. There's not as nice, or here even in mean event terms, as nice of a pattern going on. The next one is the likelihood, and it's a big smeared out.
When you say all periods, Norm, are you going all the way to 10 seconds or stopping at 3 maybe?
No, this is all of the periods that Nico used. So PGA 0.2, 0.5, 1,
Or
and 2. So just 5 periods.
The discrete ones.
Right. Okay. But this gets back to, if we want to use models and give a model a certain weight and it works for all of the periods, then we're working in this space, okay? If we wanted to work with them 1 period at a time and change the weights by model, you could work in the previous space. This makes it's easier organizationally to keep track of things when you give a weight to a model and it applies to all of the periods, but we can have model-dependent weights. Sure. Say that again? It's getting okay. Ed said it's getting clearer and clearer, and he's only been here for 1 day, so that's really good. So go ahead, Gabe. So Jenny, we're probably going to start you after lunch. Okay.
This is going back to something we talked about the first day. If you give period-dependent weights, then how do you do VS kappa correction?
And so we are doing it at the end.
You are?
Yes.
Good. Oh.
So part of our VS kappa correction, we're going to create the ground motion at the very end.
Okay.
And we're doing it in the site response part, but with clear rules. So when I
Okay.
say we, because I know I'm going to be
Okay.
involved in that part.
All right.
But I don't want to do it here. I want to do it at the
Yeah.
end,
Okay.
where I know what's come out of the whole thing.
All right.
Does that make sense? Because then I
Yes.
know what the shape is of the UHS, for example.
Exactly. Even though it may be a mix, even though that spectral shape is a little bit of a
It's a
of
mix,
mixture.
but at least then I can correct the shape that I know what the shape is.
Okay.
Because you're right, otherwise you've got all sorts of problems going on here.
Okay.
And then more correlations with the VS kappa correction, it would be correlated with each one of these different
Okay,
pieces.
so you applied on the UHS, so it's after the GMPs are run through the rock hazard. Okay, that makes sense.
So Norm, for the period-dependent weights, if that's the approach that we decided to go, then would the stencil, the regionalization, would that be carried forward? So for example, it could be established for one particular period, and then as you're going to different periods, it would adjust just like the total space adjusts. And if that's done, then it's the same set of GMPEs that are used in each of the regions. If we do something different than that, then there could be different sets of GMPEs.
Correct. You could have different sets. I think we would probably try to be keeping a single set and maybe adjusting
Right.
their weights as we go along. Yeah. Okay. Nick showed you hazard calculation from 9 models. So Nico picked 9 models trying to sample the space. He's not trying to assign weights to them. Okay, we want to start to see what are these 9, what do they look like, right, once we pick them. And I think that's part of what John was asking, show me the models, don't show me Salmon's maps, right, and what's coming out of it. So one near the middle, and then others near the edges. And some of these are pretty far out on the edges of the distributions, okay? So this is for all the periods. We can look at it one period at a time, okay? And these are, Nico, these are the same models, right? So we picked them here, but now this is where those 9 models will plot just for their PGA part, okay? So let's look at where they are. 3 was way out here over all periods. Now over PGA, it's not as far off. Okay, this is getting us back to probably the need to do period-dependent weighting in terms of looking at it. But this right now will show you what's happening. Okay, so 0 line is here. If I try to, that's this line, right? Am I kidding? That looks like this one through there. Okay, if we go to 0.2 seconds, okay, in this particular case now, model 3, man, it's really clear on my screen here. This is model 3 out here near the edge, okay, pretty far away, and we're not getting models way out on this space, even though we had that whole range sampled when we did all of the periods. Half a second. You can see where they are. The models here are tending to be with negative residuals, mean residuals. Okay, if I go to 1 second, things are actually looking better again. Okay, and then 2 seconds. So this is really pointing out a key issue for us. The period-independent weights doesn't then sample the range of each of those things naturally, and we're probably going to have to go to a period-dependent weighting, or even making sure we're getting models that sample the range of all of the space for each of the frequencies.
Norm, can you go back to the PGA? So this is the mean residual plot.
Correct.
So I remember previously you show a PGA mean residual plot that has a different pattern.
Before
so
we
what
were
has changed?
because we were using a data set that was limited to high magnitude, so we could bring the simulation data into it, right? Is that correct? Now I'm back to generating this thing over the 5 and larger. Nico, you want to answer that?
No, yeah, that's right. So this is magnitudes 5 to 8, distances 1 to 30, and the other one was magnitude 6.6 and 7.2, and then also again distance 1 to 30. So this one has a larger magnitude range in it.
So this is the one we would be using, but when we wanted to compare the simulations, because we only had them for a limited range right now, we did a smaller set, a smaller vector for which we were measuring the distance metrics, how far apart they are. Is that making sense, Brian?
I thought the original plots we looked at, this is a question for you, I think, Nico, were 5 to 8 and distances 0 to 70. No.
So that's the range where the data was, where the synthetic data was created and where the models were fit. But then I haven't really shown any maps before, but then the maps were created from 5 to 8 and 1 to 30 kilometers. Because that's like this one, because that's the important range for the hazard.
Then another set of maps was over just magnitude 6.6 and 7.2 to compare to the simulations. That was the smaller set, yeah.
So when it was smoother looking, most of the plots we've looked at up to this point were much smoother for a particular period. That was 6.6 to 7.2. Is that what you're saying? From 0 to 30?
That was two magnitudes, a 6.6 and a 7.2, and that was the only two magnitudes put in, but done over a distance range of 0 to 30. Because we had those specific simulations. He didn't build a GMPE from the simulations. He just said, here is what the GMPEs give for magnitude 6.6. Here is what they give for 7.2. And we made the comparison and evaluation just on those two magnitudes.
But when you calculate, say, mean event term, which I think is what this figure is,
Right.
you can't pick two magnitudes. You have to have a range.
Yes, that's right. So basically the mean event terms are the same in both plots, but just the positions of the individual models shift between the two plots. And the distances are much closer for the two magnitude case because then the vector is just smaller, and in general they're just closer together. That's why it gives us smoother contour.
You're not,
The underlying contours are the same in both plots.
because he's calculating the likelihood from the 1,000 models. And those are complete models, right? So he can compare that to all the data. The simulations are then just brought in Salmon's mapping where they differ, but over magnitude 6.6 and 7.2 with the underlying set of models from the 1,000 realizations. You need to use the microphone.
It's like bringing Vladimir's model into this.
Yes. Uh-huh.
So when you make a plot of mean residual, likelihood, things like that, that are using data, that those contours are based on data that's being projected onto this space from the 1,000 models, it would really help, I think, to have somewhere in the slide, here's the data range that was used. I'm still a little confused on what the ranges were that we've seen as we've progressed through the last hour or so.
The data ranges were the same,
No, they're different. This is different than what we...
but where they map into space changes, right? Because he's going to have a different set of models that he used, because this was narrower, right? So when we're looking at these simulations, I have 5 hertz.
The data that was used to generate the mean event terms is the data from the NGA dataset of Norm's model, sub 5 to 8, and 0 to 70 kilometers. That's this one. And that's the same one as was used in the other one. But the underlying map is generated from the models evaluated at magnitudes 5, in this case 6.6 and 7.2, and distances 1 to 30 kilometers.
So because of that, a point, John, in this map, one of my 1,000 GMPs is a single point sitting here. When I put it on the other map, it'll be in a different place. It's going to still grab its same likelihood, but put it somewhere else. This is nicely structured, but when I go to the other one, it looks more ratty looking. Okay, where were we? Here? So it's the same, on each point, the likelihood, the mean residual for a given realization is the same, but it's now in a different location in space. So when you look at it, the contouring of it, it looks different. That's probably the confusing part. Things, a GMPE will not have one place that it's going to sit. Okay? That's what we were saying before. If I take a GMPE, that doesn't tell me on this coordinate system, oh, okay, BSSA model, you plot at 2, and 0.5. And that's where you're always going to be. Your position's going to move because you're trying to get the relative distances between all the other models. But you have a single likelihood or a single mean residual that comes along with you, and you're going to drag that to your new location. In this case, they're not as well organized in terms of their mean residuals as they were in the previous plot, which was which had more, almost similar models. Really, the structure was, when you had that narrow of a magnitude range, all we were looking at was a constant and the distance term. So it almost collapsed the higher order dimension down into fewer dimensions already. Kim.
So I understand this a lot better now, and especially the colors, but I'm just wondering, when we plot the simulations on these plots here, for example, the XIM that was outside of the lower than everything else, does that have any information we can use that the XIM is plotting below 0 on the second coordinate, and maybe other methods are plotting either way? Does that tell us anything about how that method is performing, or is that just a function of the data space we're using?
So the fact that it's lower as opposed to higher,
right,
does tell you something. On the map, fundamentally, this says, I'm worried about how far away it is, but the directions are going to start to tell you it's, in this case, my inference would be, this is the direction of distance scaling, controlling the answer. Magnitude scaling, if I had a different, might have been in, this direction here. So you think of a thing where I have magnitude scaling, distance scaling, depth scaling, and period, and whatever it's going to be. I'm forced to put all those into 2 axes.
right,
All right? One of these is primarily the median that you're seeing, which is an important piece. And the other direction is picking up, in this case, distance scaling.
Okay.
If I had a model that came in the same as their model, but bent lower, so like a larger fictitious depth, it should be going the opposite direction.
okay. Okay, so that makes sense. Maybe we should make kind of a table on what it means to be off in one of the other axes.
So what we've talked about is putting road signs on
Right,
here.
right.
Okay? So we know what this means in these mean residuals. That's already sort of helpful.
Right.
But we want the road sign for magnitude scaling is this direction. A steeper geometrical spreading is this direction. A different fictitious depth, increasing it is that direction. So we're after the different points so that you can know how to interpret them, I think. And that's what we showed some of those at the last workshop. We haven't been putting them in here. Our focus now has been putting the underlying contours, which I think, at least for me, was a huge help to try to give me something to hang on to, okay, in terms of understanding what these models are doing. Now we can put the road signs telling me this is distance scaling, and this is magnitude scaling, this is depth scaling, and so forth.
I think that makes a lot of sense, and that gives us a lot of useful information. So maybe we're actually getting to the point where we should be computing these maps and plots automatically on the broadband platform, for example, and using them for all periods and all of these different parameters, likelihood and so on.
I think that's a really good idea.
Yeah, I agree. I think that's a really good idea. It brings together the Part A and Part B.
Right.
Yeah.
I mean, I think we understand these maps at this point so well that we can get some good information
So
out of it.
We got to write that in the meeting summary here. I'm thrilled to hear you say that, Kim. That's a success for the 3 days.
So this is, that polygon represent 1,000.
The range from the 1,000 models.
Okay. Now say if you increase it to 5,000.
It would be a little bigger.
Yeah. Okay. So. Okay.
But as it grows, what we're going to be using here is that you're going to be pushing it out of the edges of the likelihood. You could say, looking at the likelihoods here, maybe I didn't push things far enough this direction because my likelihood isn't falling off fast enough yet, right? And so then maybe I need to go to 5,000 models and push it out a little bit further. Okay, is that a fair statement, Nico? Nico says yes. So,
Okay. So
good.
those 4,000 additional GMPE, not all of them, some of them will fill up the empty space.
You mean this space out here?
Right.
Right, so right now, our concept at this point is the empty space we start out as non-allowable space because we haven't filled it out. The question is, did we really get far enough out?
Right. That's the center body of range.
Right, and so the likelihood in this, so we want to look at this likelihood distribution in several different sets to say how far can I go? Because when I'm looking here, as long as I'm moving along that mean zero line, I think was your question, how far does that extend? And that probably extends pretty far.
Okay.
But my likelihood would start to collapse, like what we're seeing on the bottom down here. I'm seeing something rounding this thing out to say that's not a zone that continues forever. What we're seeing here is we probably didn't get quite far enough in this direction to really tighten that edge up. So some of this may be still a realizable set of models over in this corner. We'd like to get it so that we talked before building our canyon or whatever around a zone that you can't go to, right? So there's some zones in here we're saying this is so far down you can't be here, and then there might be a range a little further out here before we say you can't get there. And we want to sample the space of what's allowed and not the space of what's not allowed, and then so now we've got our range. Then we have to put our weights that will establish where our center is, and whether they're symmetric or asymmetric is the body of that distribution.
No,
Steve?
this is Linda. I have a question. Well, not a question, but a comment.
Go ahead.
Since your functional form mainly it just has magnitude scaling and distance scaling, I think it would be useful. I mean, I know you're trying to do something sophisticated and putting all the information on one map, but it might still be useful to plot the old-fashioned way of magnitude scaling and then plots for distance scaling and put your 1,000 gray zone and where your selected models are, so that because people are used to seeing that kind of thing, and then people can go back and forth to these maps and understand better.
Yes. So I agree, Linda, and if I get there, I've got some plots of the attenuation. Okay.
Oh, okay. All right. Thanks.
Steve.
I know we're short on time. You discussed a minute ago, I'm going to back up, this business of period-dependent versus period-independent sampling. And I didn't quite understand what your, I didn't really understand how you could do this in a period-dependent way. And it might mean that I'm really missing something here. So I wondered if you could summarize that.
There's two ways to think about this. One is period-dependent weights. So I could create my 10 models, and then I could say, here are the weights based on where they sample in PGA. Maybe where they sample in 1 second, two of them become more similar. And so I want to adjust the weights. That's one approach. The second approach would be different models created for 1 second, and then a set of models created for another one. We're not doing that right now because we're creating a covariance matrix over all periods and all coefficients at the same time, with our goal of making spectra that look right, as opposed to completely divorcing them. My feeling right now, or belief, is that we would probably end up with at least period-dependent weights. Okay, and so I would need, in concept, I need to get, let's see if we can go through. If I wanted to sample this space in PGA, I could create a set of models, and I would need to go a little further out, let's say. When I go here, I might now need to make another set of models. I hope some of those models are overlapping so I can find one that's common and I don't have to make 50 different models. But you may find one model is, I adjust the weights for models where in PGA space, let's say I'm trying to do 2 periods and I make 10 models for PGA and 10 models at 1 second. Then I plot them together on the PGA map. Maybe some of them will be close together here. So I could say, yes, they're all covering a range, but I'm going to divide their weights by 1/3 because 3 of them are essentially the same. But in PGA space, they're separated, and now they need to have a different set of weights because we need our sets of models to capture the whole space, right? Not just the space in all periods at once. This was, I think, our right concept to start from, and then we can see where that gives us difficulty, because this is measuring the distance between the models as aggregated over all periods at once, where they may be really close. 2 of these models could be very close at PGA and very different at 1 second, and then they show up as a different point, but when I go to the PGA, I've got the same model again.
So you envision using a set of GMPEs, and then but you're using a different linear combination of them at each period.
Yeah,
or weighting them,
Yes.
different set of weights of
Correct.
them. Different
Correct.
weighted combination of them at each period.
And I'm trying to keep that from being 10 times 20 periods, right? So I want to make this, I could make 10 models at every period times 20 periods, and I got 200 models. It doesn't affect the hazard run. It's the same effort because the hazard runs them independently. It's now a bigger bookkeeping exercise. But to the extent I could reduce that down to 30 or 40 maybe that are common, and then set the weights up so that it makes sense for sampling each of the periods one at a time.
Is that throwing out any of the expert judgment that goes into building the GMPEs in terms of assumptions about smoothness across the spectrum?
It's not throwing it out because the model is still created over all periods. So we have that model over all periods, but we will say your model over all periods is the same as this other model over all periods. I don't want to give you the same, I don't want to distribute the weight. But let's say they were equally weighted in PGA space. They may not all get equal weight in the 1 second period space in order to still capture the full range. We do that, that's not unprecedented. We have done that before, and we deal with models and say these models are working well at short periods. At longer periods, it's maybe less data or less well defined, or it's missing a quadratic term in magnitude. It doesn't work at long periods, so that we would downweight them. So that's not fundamentally different. It is it's more effort on our side to try to keep track of all of that. But I think this is showing us the idea of a single set of models selected in all period space domain isn't going to work very well. That's really the conclusion from this. Ken?
Yeah, so if you do that, then I think you're going to have another set of plots that sort of looks at the spectral,
Shapes.
the spectrum itself, not just magnitude scaling, distance scaling. Now you're going to have to look at spectra to make sure shapes are reasonable and cover the space.
Correct,
Right?
but we are maintaining the shape of each model. So that's created. We are not, let's say you were doing a spectrum and you had 5 models, and you said there, I give equal weight to all of the models at high frequency, but I give higher weight to another model.
Okay, so the weighting is only going into calculating the hazard, so it's a little hard to know.
Yeah, you could look at the weighted average of the shapes and see what comes out.
Yeah, somehow you're going to, I think you need to
Yeah.
be able to visualize that, not just in, because in the hazard space, it's going to be very difficult to
So we're
understand.
almost into lunch. I want to show you some pictures that you'll understand again, okay?
Norm, can I do one quick
yeah.
question here?
Yes.
For each of those frequencies, the maps are created using the 7 GMPEs fitted to the common functional form, right? At each different period.
They're not, but they're generated, the common functional forms are generated all the periods at once. Because the covariance matrix, remember, had a whole set of boxes. One box was for the coefficients at PGA, and then we had the cross terms between the PGA and the 0.2 and the 0.5. So all of those coefficients are in there at once. So when Nico makes these, he makes an entire model at all frequencies.
But you can do them at one frequency at a
We
time?
could, but we don't want to, because we wanted, just the issue that Ken said, we want to be sure we're getting a spectral shape out that is still consistent as well.
So would it be possible to, say, start with one frequency, make the map, and then if you already have the algorithm defined for selecting the models based on a map, then go to the next frequency with those selected models instead of the original ones? Go to the next period?
Yeah, and we could see where they fall, and we may need to select some additional ones. Right. But, so that's a way to avoid building a larger number.
Yeah.
As I said, in the end, it makes no difference on our hazard runs, because the hazard is run one period at a time, independently. But it does help in this whole concept of correlation. We had talked before across period and for given models. So I think it would be good to reuse a model as much as we can across the period range. And I bet that will work. We may then have to, though, instead of 10 for all periods, we may have 50 models, and not all of them are run at all periods. You know, I could pick out 10 of them for each of the periods.
Yeah, well, I was thinking maybe even if you went through one period at a time and you had your algorithm set up, when you were done with the set of periods, you would select the final set, and that would be your set.
But you probably can't find a model that samples the range that we want to capture in PGA, and then have the same model sample a range at 1 second. That probably won't work. Okay?
Yeah, I wasn't necessarily thinking the same model, but I was thinking at using the models that were selected for the next period. Maybe we can talk after.
I don't know what that sounds like the same models, though.
Yeah. We can talk after.
Yeah, let me get to these plots, then we need to stop for lunch, okay? But I wanted to show you some plots that look familiar, okay? So this is just the 9 models that were generated, okay? So this is for peak acceleration, so that you can see what's happening. Remember, we were only using them less than 30 kilometers. So whenever you take, if you generate coefficients over a certain range and extrapolate it, things happen, right? So you can get funny shapes, and so you're going to see at the larger distances, these were only generated out to 70 kilometers, stuff starts to go out. When Nick ran the hazard, we just chopped it at 30 because we know nothing contributes, just to avoid any of these problems. So okay, I'm going to jump all the way to make Yusuf happy. So so these are the NGA models, or the not just those, but the candidate models in green, and the generated models in gray. Okay, and so these are ones that Nick made, and so at magnitude 5, we're near the edge. We haven't picked them all up. In the magnitude 6 range, they're all inside here. So this is telling me right now the way that we got these didn't pick up a big enough range of magnitude 5 scaling. Okay, you can see the magnitude 6 scaling is pretty well captured. Again, focused only on the first 30 kilometers. So we broaden the range. If I go to magnitude 7s, they were already really tight, and then the range is broadened out here. magnitude 8 is in here, and now I've got, is that Zhao's model going up? And we didn't get there. So, oh, Idris. Yeah, Ed, that's your model at short distances. That's really popping up. So when we go to 1 second, so just so you can see what's happening at 1 second, here's the range on the right of magnitude 5s. Here's the range at magnitude 6. Now remember, at 1 second, we're not getting all around, okay? So when we picked these 9, it was in the space of all periods at once, and that's not going to work well, okay? Magnitude 6, you can see what the ranges are here, and then magnitude 7s and magnitude 8s. So this is back to, we can see here, we don't have enough going low. If I went all the way back to my maps, where was I at 1 second? Okay, so I'm not sampling completely what I wanted to cover, and there's got to be a direction, probably in here or in this direction, that is not picked up on that low magnitude scaling. In fact, that would be towards the positive values, positive residual. So I probably got a hole in this range or on this side that's not giving me low enough magnitude 8 scaling. So let's stop for lunch because we're already 10 minutes over. We'll start up again at 1:10. We should be okay, so go ahead and take an hour for lunch. We're going to shift back to directivity. And then when we're talking about the reverse case, Bob is going to just be giving you a general approach. We don't have the numbers run. If you have more questions about this stuff, we can come back to it. Drag Nico back up here one more time. But I am encouraged that this is starting to get somewhere with everyone. All right, thanks.